All right, let's dive right in. We're looking at a really important piece of the infrastructure puzzle today. How do you get that legacy CATV signal, that traditional radio frequency, onto modern high-speed fiber optic cable?
Right, the classic RF over glass problem.
Exactly. And our mission for this deep dive is to really unpack the engineering behind one solution, the Thor Broadcast F-RF-1310-TX transmitter.
And this device is, well, you can think of it as the ultimate interpreter.
An interpreter.
Yeah, it has to take that entire bulky RF signal, we're talking everything from 45 to 870 megahertz, all your channels, and convert it. But what's really fascinating here is that it converts the RF signal directly into an optical RF signal.
So we're talking about standard RFOG.
Yeah.
And by putting that whole channel lineup on just a single fiber, you're immediately unlocking some serious scalability, correct?
Absolutely. That one fiber becomes your distribution highway. It makes these complex point-to-multipoint applications, where you're feeding a whole neighborhood.
Using passive splitters and things like that.
Exactly. Using PLC couplers and splitters, it suddenly makes it not just possible, but actually economically smart.
Okay, so that economic viability must depend almost entirely on the optical output power. This unit is pushing 16 milliwatts.
It is, at a very precise 1310 nanometer wavelength. And that 16 milliwatts, that's not just a random big number.
Right.
It's your power budget. It dictates how many times you can split that signal and still have enough juice at the other end.
So it's all about reach.
It's all about reach. And to keep that stable, they use a highly linear DFB laser with automatic adjustment circuitry built right in.
So if the laser is the precision engine, then the automatic gain control, the AGC, that must be the smart driver.
Precisely.
Yeah.
And that's a huge win for you, the person installing it. The AGC handles this huge range of RF power on the input side, from 11 all the way up to 29 dBmV.
So you can just take the signal right off a tap without having to mess with attenuator.
You got it. It just eliminates all that manual guesswork.
Okay, so we've got the power, we've got the stability. The next big hurdle has to be signal quality, especially over distance. The sources cite some pretty serious metrics. CNR greater than 50 dB, CDB less than -63 dB. What are these numbers actually telling us about the end-user experience?
They're telling the story of a pristine video feed. So, CNR, carrier-to-noise ratio, that's just how clear your signal is compared to the background static. Over 50 dBd means your picture is sharp, even after 10 kilometers of fiber.
And the CGB and CSO?
Those are distortions, composite triple beat and composite second order. They measure things like ghosting or weird lines in the picture. Getting those numbers that low means you're getting a really clean, stable feed, perfect for HD.
Beyond just a clean picture, the source material really emphasizes a security advantage. Let's drill into this fiber break concept.
Yeah, this is maybe the biggest upgrade over copper. See, traditional COPS has a return path. It's used for interactivity, maintenance.
But it's also a weak point.
A huge vulnerability. By creating these high-security fiber breaks, you eliminate that return path entirely. It creates a one-way unidirectional link.
Which means you can't inject a signal back up the line.
Exactly. It makes tapping the line, which often relies on that return path, almost impossible without physically getting to the fiber.
A massive leap in signal integrity. Now let's pivot to a detail that I have to admit I find fascinating. The input is easy. Standard type F.
Yep.
But the optical output is incredibly specific.
It is vitally important. The unit must interface with an SD-APC connector.
And the key there is the APC, the angle polish connector.
That's the one.
So what happens if you ignore that? What if you just use a standard flat connector?
Well, you get chaos.
Yeah.
Total signal instability. Think of it like this. A flat connector is like shining a flashlight straight into a mirror. The light bounces right back where it came from.
Back into the laser.
Right back into the laser, causing havoc. The angled polish is like tilting that mirror just a tiny bit. The reflection goes harmlessly off to the side.
And that maintains the return loss spec, keeping the signal clean.
Greater than 55 dB. It's a non-negotiable detail.
So if your existing fiber network uses a common flat PC type connector, like an SC or an ST, you can't just plug it in.
Absolutely not. The sources are clear. You must use an optical jumper to convert from your flat connector to the required SC-APC type. That one tiny detail is the line between a perfect signal and complete system failure.
It just drives home the complexity, doesn't it? It's a bridge device, taking old RF signals and launching them onto this new fiber infrastructure.
It's the essential interpreter for this whole transition.
And that makes you think. Considering the absolute necessity for something as precise as an angle-polished connector just to manage light reflections, What other hidden high-precision requirements exist in the seemingly simple transmission of video and data that we all take for granted every single day? Something to mull over until our next deep dive.